So much for the invitation in this nice place. So my talk will be mostly algebraic, but the program is supposed to be in quantum topology. I hope we will see a bit, I will shortly say a bit of representation theory beyond this, and possibly for people in categorification, we could expect some inspiration on categorification. So, first I should say that this is a program whose first step was work with Martin Palmer and Avaïs Chocat, and we are a project with Alexei and Anna. So I will focus here on definition of those Heisenberg homology for even graphs and certain computational express rates. So first motivation is that most people here are interested in quantum invariant. So my motivation is the question about quantum invariant versus classical. So from algebraic topology, you know those classical invariants like Euler characteristic, homology, torsion, Alexander polynomial. And from quantum construction, we know a lot of so-called quantum invariants, starting with Jones polynomial, Carlot-Jones, for links, Reshetikhin-Toureyev for three-manifold, TQFTs, link homologies, if you think about categorification. And the general goal of the program is to consider classical construction for this quantum invariant. And in this talk, I will focus on representation of mapping class groups. And as further motivation, we are expecting extra structure and application from homological construction. And on the categorification side, we expect to be in a picture which will be available for Fleur-Fukaya construction. So first, starting with old stuff. So in the 90s, Rick Lawrence defined a family of representation of the classical grade groups. And these are defined as action. No. Should be a pointer, the other side. No, whatever.
Otherwise, you have a stick there.
Oh, you have a stick, perfect. So we are acting on homology of configuration spaces with local coefficient, or explicitly, if you want to be down to earth, on certain covering space of configuration in the punctured disk. So this is something quite easy, well known. Then, so this is a Z2 curve. And the famous theorem by Bigelow and Kramer in the early 2000s was from this to obtain linearity of braid groups. So, and the Bigelow proof is a consequence of the fact that for n equal to, this representation is faithful. And the challenge, so this is for homological construction, and this is connected with quantum, indeed, from work of Kono and Jackson-Kerler. These Lorentz representations are equivalent to SL2 quantum representation restricted to highest weight spaces. So this is quantum. And now we are working with several people on the higher genus case. So first we considered the case of genus G surface with one boundary component. And because the red group is a mapping class group, we expect similar construction in higher genus. And the first step of this program was to obtain LKB, so the previous rate group representation, similar representation for the modular group in this case, from homology of configuration space in the surface with certain local system. I will explain a bit local system, but it comes from essentially from a curve as before. And this local system can be any representation of an Heisenberg group, which I will explain. So it's not commutative, it's not an abelian curve as before, but almost. This I will explain. And the second part, the second step for this is that this contains quantum information. So there is a strong paper by Marco de Renzi and Jules Martel, and they prove by computation, by comparing the basis, that if you specialize V to be a certain finite dimensional Schrödinger representation, if you know, that's perfect. If not, say that exists such a representation, on which you have an action of the small quantum SL2 on a sum of those homologies, those ones, the sum of all n. So you have a quantum group action, so it's quantum. And second, you can extract a sub-representation which is isomorphic to the G power of the adjoint representation. As a quantum SL2 module, so as a representation of small quantum SL2, and as a representation of the modular group, of the mapping class group, and this representation is known to be a TQFT representation from the construction of a non-semi-simple TQFT representation, first defined by Kerler and Yubashenko. So we consider similar questions of action, homological action on mapping class group, and in a way, we know that this is quantum. So I will come back down to Earth and try to explain a bit of this. In the case, I will consider the case with more binary component. Questions so far?
Sorry, a question. Is V a local system on the configuration space?
Yes, V is a local system. So that will be part of my explanation that any representation of the Heisenberg group gives you a local system of the configuration spaces. It will come very soon. Thank you. The global picture should be clear. Now, technical, some details. Let's start down to Earth. So our goal is, in the case of surface configuration, get for sigma gm. So it's a technical point that the boundary should be non-empty. Something can be done with empty boundary, but you should add something. And I don't want to be too technical, but I know how to do. So then we will consider homology groups on the configuration spaces. And we expect a combinatorial description when we take a ribbon graph, a surface associated to a ribbon graph. So start with the surface braid group, which is the pi1 of this configuration space by definition. And if you take a representation of this pi1, as mentioned by Misha, we have homology with local coefficient. And if you do not know too much about this, just say that you take the universal curve and you tensor with the representation of the action by deck transformation of the pi1. And this gives you a complex, and the homology with local coefficient is, can be defined like this. This is my preferred definition of homology with local coefficient. So this is quite basic in algebraic topology. Maybe now people are less used to this, but this should be clear since all my construction will rest on this. So homology with local coefficient. You can just, if you are, you could forget about this and say just homology of certain curve, either universal curve or intermediate curve. But the general way is to tensor product with deck transformation with a certain representation. Okay, this should be clear. So now, I will also consider the Borel-Moore homology variant, which is homology with locally finite chains. And it can be defined as a limit where we consider homology relative to the complement of a compact subspace, and we take a limit. If we replace homology with cohomology and take the limit in the other direction, we would have cohomology with compact support. So this is natural. You should think about this as homology relative to the boundary at infinity. And in our context, it will be more convenient. So then, this Borel-Moore homology is functorial with respect to proper maps for which inverse image of a compact is compact. And then, for a proper embedded, you also have relative Borel-Moore homology, as usual. But it should be a proper embedded. So now, about this surface braid group. So you take a base configuration, and in this base configuration, you take the first point to be the base point in the surface for the pi 1. And then you have this model. So this point is my base point on the surface, and these 3 points represent my base configuration. The base configuration is a set of points in the surface, unordered. So here I took n equals 3 and put 3 points on the surface, which represents the base configuration. And then we can, so a nice presentation was set up by Blanchet. The presentation was done before, but this one is really convenient. So think that you have a classical generator, changing locally 2 points, and you have a pi 1 generator. So the pi 1 generator, if we come back, here we have standard curve alpha I, beta I, and gamma j, represented basis for pi 1. And if you move only the first strand of your configuration and don't move the other one, this gives you a braid. So this I will call a pi 1 generator. And then with those generators, we have, quite nice presentation. So these are the classical relation in the classical braid group. Here you have certain commutator relation which are easy to check. And I would focus on the last one. So if I have time, I draw this relation, but I will not here. It's easily checked, but the observation is that it is, in some sense, non-homogeneous. So that was the starting point for this project. That if you want to mimic Lorentz representation, you are looking for an abelian local system. So an abelian representation of the braid group. But here, if you abelianize, you will get sigma 1 square equal 1. And this is not good. This means that you are losing all the information about configuration. But of course, if you almost abelianize, you can get something non-trivial either. And this is the main point. So just focus on this relation. And then we come to this Heisenberg group. So this will answer Misha's question. So the Heisenberg group in genus G is the central extension of the homology defined with the intersection cocycle. And as a set, this is Z times homology, and the law is corrected here with the intersection form on the surface. So this is an explicit description of the Heisenberg group in genus G. If you take G equal 1, you will get your favorite Heisenberg group. Maybe another model, but it is, you can draw this group as a matrices. And then an easy theorem from the presentation is that if you quotient the surface braid group by the normal subgroup generated by commutators with sigma 1, then you simplify your previous presentation and you get a presentation of the Heisenberg group. So from this remark, any representation of the Heisenberg group will become a representation of the surface braid group and will give you a local system on the configuration. And we should be careful that it is isomorphic as an abstract group, but the isomorphism is not canonical. It comes from the presentation of the surface. You should think here that you may be an ambiguity through automorphism of the Heisenberg group. And an explicit isomorphism send sigma I to the central generator, the generator of the extension, which I denote by 1, 0 in this model. Okay, so this is in the kernel of the extension. A pi 1 generator is sent to an element which is given by the homology class of this pi 1 generator. And it's easy to check the relation. So we have an explicit isomorphism, but I focus that if you change your model for the surface, you will move this by an automorphism of Heisenberg. So it's not canonical in some sense. So given such representation, we have homology groups, standard homology, or Borel-Moore homologies. And if we denote with a tilde the regular carver associated with the kernel of the quotient map, so the normal subgroup generated by the commutator with sigma 1, then we can consider the chain complex of the Heisenberg carver, chain or cell complex, depending on your favorite model. And by deck transformation, it supports an action of the Heisenberg group, so it's the H module, right module. And you can rewrite your chain complex for the local homology as you can replace the previous universal carver by this Heisenberg carver, which will be a bit smaller and more manageable. So you could just, in first step, you could just consider homology of this Heisenberg carver, which will be very similar to what I said with Lorentz representation. And then we consider action of mapping classes. So if we take a mapping class, we apply the configuration functor, and we will get first an automorphism of the Heisenberg group. This is what I said before. I will not give formula for this, but this is not difficult. This is kind of lift of the symplectic action, the homology. And it's because the kernel of the quotient map from braid to Heisenberg will be respected. This is easy. Then this configuration of your mapping class lifts to the Heisenberg carver. And this will induce a chain map on the configuration, on the lift of the configuration. And of course, this chain map will give you an homology map, but at the level of the Heisenberg curve, but at the level of the local system, you should be careful, because this map will be C-linear, but over H it will be twisted linear by FH. Because you have, you should think about it, that you have this action, deck action, and so as a module of Heisenberg, this will be twisted linear. And you can compose your local system given by your representation with this automorphism. And this is one delicate point here. You will change the local system. And it's natural to denote this local system with FH index on the left, meaning that when you do the representation, you pre-compose with this automorphism. And then you get a twisted action that over a change of the local system by this FH. But indeed, this is a representation not of the modular group, but of a modular groupoid. If you want, if everybody like categories and functors, so it can be formulated this way. It's not a native group representation, but by the way, we will show later that with a convenient V, this can be modified so that it is indeed a native action. So we have, in a twisted sense, in all cases, action of mapping classes on this homology. So this was a quick setup about Heisenberg homologies and, in general case, action of mapping classes. So now we switch to ribbon graph. So is it clear for this general picture about construction of homologies using Heisenberg curve and corresponding local system? All these homologies I will call Heisenberg homologies. Okay, an Heisenberg homology, which was in my title, is homology of a local system which factorizes through the Heisenberg group, local system and configuration. So now I come back to ribbon graph. The ribbon graph is a graph with ribbon structure. I start with a graph with ribbon structure, which is a finite graph with a cyclic ordering at each vertex. You have a cyclic ordering of the jump of edges. And from a ribbon graph, so the ribbon graph here is blue. And the cyclic ordering is given by the embedding in the plane. And then from this information, you build a surface by thickening in the plane or with respect to the cyclic ordering. Meaning that you take one band, full band, because we will have relative version afterwards for each edge, and you glue them according to the cyclic ordering along the half end of the edges, corresponding to the edges. And this is the surface which is called the ribbon graph. Okay. So now we may consider the unordered configuration space of the graph as a subspace in the surface, which I think with the previous local system. And we also have a graph braid group, which comes with a natural inclusion map to the surface braid group. And so, by using this inclusion map, the previous local system restricts to the configuration in the graph. So the question now is, can we say something about the homology of configuration in the graph, which would like to be rather combinatorial, and homology of configuration in the surface. We will have also a relative version of this. It's useful to have a relative version. This notion is relatively new. For me, it was inspired by work of Norbert Acampo on a tête-à-tête graph, if you know about this. So a relative ribbon graph will come with a subgraph A, whose components are oriented circle or interval, and the cyclic ordering should be compatible. And compatible, maybe the best is to look at the picture. The compatible means that at a vertex in A, for example this one, an incoming edge will be lost here in the cyclic ordering. So the cyclic ordering is a sequence like this. So the incoming edge is lost, and here it's first. So this compatibility condition ensures that you get an oriented embedding of A in the boundary of the ribbon graph. And the example is easy. So now the ribbon graph is constructed with full bands and half bands. So this edge, which was previously in the middle, is coming to the boundary.
Is all of A lies on the boundary?
All of A should be in the boundary. Yeah, all of A will be in the boundary. So this is part of my quick definition.
And that's why you can speak about first and last.
Yes. Yes.
Okay.
Do you also have an orientation of every edge in A?
No.
Of every component?
No. I will need orientation of these edges when I will like to fix a basis, but formally I don't need. The oriented surface is defined with the edges and cyclic ordering. But I need the compatibility on the boundary, so the orientation is given for the subgraph. It's fixed.
So the orientation is induced by the orientation of the surface?
Yes, yes, yes. This is what I mean, but you get an oriented embedding of the subgraph in the oriented boundary. So your surface is built, your recipe is to take bands and half bands to glue according to the cyclic ordering, and you do this in a way that oriented A is oriented part of the oriented boundary. So now we take a sub space of the configuration, which you think as part of the boundary in the configuration, where you have at least one point in the subspace. And I will denote this by conf n of gamma, gamma A. So this is part of the boundary in the configuration. You should think that configuration is an open manifold. You have points at infinity. You have a boundary part when the configuration meets the boundary. And in this boundary part, you have a special one, a special subspace, which is denoted with a pair. And you have the first theorem. So this theorem is called the compression trick. And I think the idea comes from the computation at the beginning by Bigelow. It should be adapted to the case of surfaces. You should be careful that, let's do the statement. So we do the inclusion of configuration graph configuration into the surface configuration, and we take local coefficient compatible with a representation of the surface Gray group, and then you get an ISO on Borel-Moore homologies. This is quite a strong statement, which says that you can compute with combinatorics of the graph. And the idea of this is, you remember that Borel-Moore homology was relative to the complement of the compact. So you fix an appropriate distance on the surface, and you consider the retraction of the graph. You have a natural retraction on the graph. So you put a distance so that this retraction is always a contraction. And then you use first nomotopy equivalence corresponding to this deformation, retraction by deformation, but you cannot go to the till the graph because you will have collisions. But if you make your ribbon graph small enough and you compact to be defined by a certain distance epsilon, such that you have at least 2 points in this configuration which are very close, then you can continue with an excision on the collision locus. Well, it's a little bit technical. I really give you very quick. I totally realize that you cannot get the full proof just with this remark. I just say it's a mixture, very tricky, between deformation and, at the last moment, an excision argument. And it works because it's Borel-Moore. By the way, it's not formulated anywhere, but this argument will work for the cohomology with compact support also. So behind this story, you also have cohomology.
So, sorry, Christian. Again, what is conf n sigma gamma? What is conf n sigma gamma? No, on the right.
This sigma gamma is the ribbon surface associated to a graph gamma. Gamma is a graph. Sigma gamma is a surface.
They're just all points on that surface. All configurations.
Configuration is that surface.
Points on that surface.
So you are comparing homology of configuration in the graph, which is combinatorial, and homology defined at the beginning for configuration in the surface. And the small miracle is that you get it.
Pi 1 of the left hand of the space on the left hand side is much simpler than pi 1 on the
it could be that in many cases pi 1 is the same. It's not obvious, but in many cases pi 1 is the same. In the stupid cases where you take a circle, this graph could be 2 points making a circle, then on pi 1, the pi 1 will not be iso. It's easy to consider the braid group inside a cylinder and work out the presentation, and you will check that in this case the pi 1 map is not iso, but in most cases it's an iso. If you replace, so in this case you will not get an iso, but if you do this, you will get an iso. Pi 1 of sorry, Bn of this graph and Bn of this graph are not the same.
Bn means braid
the braid group. The braid group.
But it's almost trivial for the left graph.
Here it's a Z. You take 2 points, you take 2 edges, and you can just rotate. The generator will do this. You take this as the base configuration, for example, of 2 points. If you take 2 points, it will be Z.
For the graph on the right-hand side, it's high.
This Bn of this one will be the same as Bn of the corresponding surface, because you can always put 1 point here and go through.
But the surface is an annulus, or what's?
Here, the surface is an annulus, but here the surface will be like this. So it's an annulus topologically. So the surface here and here are homeomorphic, but the graph are not.
So saying the affine braid group is isomorphic to pi 1 of the graph, pi 1 of the configuration space of the graph.
The pi 1 of this graph is isomorphic to pi 1 of the graph of the surface. Of the surface, of configuration in the surface. Okay, you have certain subtlety like this, but even when the pi 1 is not the same, this theorem holds. You can still restrict the local system to the configuration in the graph and get this iso.
What do you use cyclic order on the other side? There is no, like if you have a graph, then this...
If you have a graph, here you have a cyclic order which you put the orientation of the cycling. You need to fix the orientation.
I see. But for the configuration space, it doesn't know about the cyclic order.
The configuration space on the graph doesn't know, but the local system does.
Oh, okay.
This is a good remark, very good remark. The homology will depend on the local system. Also, the graph, the homology, standard homology does not see, the homotopy type doesn't see the cyclic orientation, but the local system does. Okay, this is what I say here. Rho composed with the exclusion map defines the local system on the Graff configuration. And there is also a relative case where you take configuration relative to part of the boundary. Borel-Moore configuration relative to part of the boundary. And you also get this. So now we know that we are reducing computation of Heisenberg homology of surfaces to combinatorics of the graph. What about the combinatorics of this graph? And this is where I will introduce a Borel-Moore cell complex. If you take the usual cell decomposition with compact cells, each time you have an open space, manifold, you will have infinite cell decomposition. But here, we will change our mind and say maybe we can have a nice filtration where the decomposition at each step will give you cells, but these cells are just attached to the previous skeleton on part of the boundary, not the full boundary. And this is quite natural. Why? So it's good to have a certain idea at the beginning. What is C2 of an interval? Configuration in an interval. This will serve as a model for our open sets. So this is just take the square and quotient by the S2, the transposition. So this you remove and you get a simplex. But in this simplex, this is boundary, but this is at infinity. So C2 of an interval is a simplex, but it sounds sense if you think of this as a proper simplex which will be glue. If you use this as a cell, you will glue to the previous skeleton on these edges. This will go to infinity. So this is what I want to generally define here and use in a way which is similar to the usual CW complexes for computing the homology. So this is the goal. So I start with a finite graph where S for sommet are vertices. I do not use V because of the representation, and E is the set of edges. And I will say that, for example, in the case n equal 2, I want to describe the configuration of 2 points. And for this, I will have 0 cells which are pairs in S. If S has cardinality 1, there will be no 0 cell, but it's not a problem. You should think of this as similar to a relative CW complex, which can have no 0 cell. And the 1 cell are edges which are paired with a vertex. And I think about this as subspace in configuration of 2 points. And I will have 2 cells which are either squares, product of 2 different edges, or simplices as before, configuration of 2 points in edge. And when I take configuration of 2 points in edge, it's a triangle with the diagonal with 1 edge removed. And in general case, I will start with kind of the 0 skeleton of my configuration, which are just n configuration in S. And for each k, the k skeleton will be the union of the k minus 1 skeleton as before, and the k-dimensional cells, which are product of simplices, indexed by subset with cardinality k0, and edges, product of configuration in edges, so that the dimension is n minus k0. So these cells are product of simplices. And this way, I get a skeleton filtration on my n-point configuration. Okay. I'm adding at each step cells which are half open and which are product of simplices. I mean, they could be closed in this way. Even here, it's yeah. Say half open cells. And the Borel-Moore cell complex. The K cells are attached along the faces which are not diagonal, of course. And if we fix an orientation of gamma, then the cells are oriented, and we have, as usual, incidence signs on the faces when we glue, as usual, plus or minus 1. So that we get a Borel-Moore cellular chain complex, which is this graded module generated by the cells with boundaries given by incidence number. So this will compute, it's easy, it's similar to the usual case, the standard homology of configuration. Now I want to do with local systems. For example, if you take an oriented edge, it has boundary W minus V. And you have a boundary of the edge U times E. Sorry, this should be S. Here I didn't change. This should be vertices. So the boundary will have 2 points if U is not one of V and or W. But you can have one edge with only incoming, outgoing boundary point, because the other is going to infinity. You cannot, here in this situation, if U equal V, the UV configuration is excluded, it's in the diagonal. Or if U equal W, you just get the incoming point. So U edge, it's clear here. Here, if you take this, the boundary here, this is at infinity. So the boundary of an edge may have only one contribution. So with local coefficient, if you have a representation, you can lift the cell decomposition to the cover and play as usual. And you get a complex where your incidence sign is corrected as usual by an element of the deck group. And this way, the Borel-Moore homology is canonically isomorphic to the homology of the cellular chain complex. Sorry, yeah, okay. So this is my chain complex. This is the cellular chain complex in the Borel-Moore cells. This says that the Borel-Moore homology of the graph configuration is combinatorial. You have a finite model.
This is for any representation of the prey-group of the mapping class group.
This is any representation here. You can take Heisenberg, but this is true for any representation.
But you're saying for sufficiently complicated graphs, you have an isomorphism between Bn gamma and Bn of the surface.
Yeah, here you have no sigma. So this is always true. This is a statement in graph theory.
But you're saying that for many graphs, Bn of gamma is isomorphic to Bn of the thickening.
Yes. Yeah, Bn is isomorphic to Bn of the thickening, but this doesn't mean that this is true for homology.
Okay. But the pi ones for many graphs As long as you have enough legs, they are isomorphic.
Yeah, yeah, they are isomorphic.
You need enough legs for something.
Yeah.
Sorry, so if you take 1 point compactification of conf n, so then these cells will become like the actual cells in 1 point compactification.
I don't think so. But here you should be careful because the one point compactification is not good for local systems.
I see.
You cannot expect.
Can I also ask if are you using this kind of little edges to kind of some kind of stacks where you can hide the point, move another point along it, and then move it back? Is it some kind of memory devices or storage devices?
If you put this small air everywhere, you will get the same pi 1.
You get the same pi 1.
You don't need a lot. I didn't work a lot for
You
this.
just need only one? You
Only one should. Then the world will be complicated, but yeah. But I didn't work this a lot. So you also have a relative version, where, of course, the relative Borel-Moore cell complex is what you think. And this way, you can consider this model surface. So here, my A will be the blue thing. And then, maybe here it's not completely, I do not have the band. I took another picture, but you understand what I mean. You graph with the blue thing and this purple one. So the vertices are just here. And the graph, the A subgraph is this boundary minus part. And the edges are the gamma I. And then I can apply this and say, I am in the case where the relative homology of configuration in the surface is isomorphic to the relative Borel-Moore homology of the graph. And the cell complex for the graph is easy. And I get that this relative Borel-Moore homology is isomorphic to a direct sum of 2G plus n minus 1. Sorry, this is the case where I have one boundary component, but I can also correct and have general case. So you get just copies of V, because here the relative cells are just product of configuration in the gamma i's, and you just count them. So you can compute this case. And this case was computed elementary before this Borel-Moore complex setup, but it's an example. And now I'll go to the last part. So I said I finished with the ribbon graph configuration. So if I summarize, we like Heisenberg local systems. We try to convince ourselves that we can compute some using the configuration, the combinatorics of configuration in graphs, and this Borel-Moore cell technology. And now let's try to come back to the use of this and possible connection with quantum. And then we will come back to sigma G1, take P an odd integer, and take a finite quotient of the Heisenberg group. For technical reason, I restrict to odd P, but we can also do something with even P. This is just to be simpler. So then, if Q is a P root of unity, this finite Heisenberg group acts on a finite dimensional Hilbert space. Very quickly for algebraists here, and there are many, you can construct this representation by fixing a character on a maximal abelian subgroup in finite Heisenberg. So in finite Heisenberg, if you take a Lagrangian head center, you have a maximal abelian subgroup. You take a one-dimensional dimensional of this and you induce. But if you do not know about this, in the case G equal 1, you start with a basis for homology. Then the Heisenberg has 3 parameters in genus 1, and you can fix a basis for this WQ, and this will be my Schrödinger, and you get explicit action of the generator of the Heisenberg group. And you see that you have a central charge, which is the quantum parameter. In your value, this is the starting character. You have the longitude, which is acting by translation, and the meridian, which is acting by modulation. And this is a standard picture for Schrödinger representation. And then, in this case, you have this famous Stone-von Neumann theorem, saying that if you fix the central charge, then this Schrödinger representation is irreducible and unique up to unitary isomorphism. So it's unique up to an S1 complex number. So the fact that it is unique means that when you change, when you compose with an automorphism of Heisenberg, you get up to ISO the same representation. So this way, our twisted representation of mapping class group will act no more by going from one space to another space, but it will act by automorphism. So this is what we say now. The Stone-von Neumann theorem provides a unitary isomorphism from this WQ, or Schrödinger, favorite Schrödinger representation, to the twisted Schrödinger by an automorphism. This is defined up to a scalar. And this way, if you compose the twisted isomorphism defined previously with the coefficient isomorphism coming from Stone-von Neumann, you get an automorphism of homology of configuration with this local coefficient. And because of the S1 ambiguity, it will not give you a completely native action of the modular group, but just a projective action. But we are fine with this. This is usual in TQFT. A projective action, it's an action of a central extension, and this is easy to understand. So we get a native representation of a central extension. We are able to identify the co-cycle of the extension, so the class. And this is the same with Borel-Moore relative variance. So this construction with Schrödinger representation gives you representation of central extension of modular group for all the variants of these homologies. And this is where we are recovering quantum representation. So this is a huge work of Marco and Jules, where they are constructing an action of all of small SL2 on the sum of the homologies for this variant. This is the variant I computed. And you take the sum of all n, this is the big space. But moreover, if they take the truncated sum, which will be finite dimensional, you can extract a sub-representation which is isomorphic to the G power of the adjoint representation. So in the genus 1, you recover the adjoint representation. And they are proving this by comparing action in the basis. This is quite involved. And you get something which is isomorphic as SL2, quantum SL2 module, and as a projective representation of the modular group. And this representation is known to belongs to a TQFT. This is the non-summissible TQFT, where the projective representation was first constructed by Kerler-Dubashenko. So this stuff, which is completely algebraic topology, contains quantum. This is part of quantum topology. So this is very strong. And now, with Alexei and Anna, we are thinking about action of cobordism. And what we are able to prove is that, of course, if you use mapping class, we saw that we have action on the local system. So the first question, if you want to extend to TQFT, is about understanding action of cobordism on the local system. And more or less we understand this, and it is very close to abelian TQFT. I will not give details, but we have a paper with Alexei and Anna on archive where we study this. And we expect an action of cobordism on Schrödinger homologies. Meaning that we expect that from this construction we will produce a full TQFT. Now, for you guys, here are some questions of problems. One problem, I mean, with the graph I cannot compute all. In particular, I cannot address the absolute Heisenberg homology. With this relative picture, I got part of the boundary, but not the full boundary. So it's a small question to understand the absolute Heisenberg homology. I should say it's not a big question. I even could say that probably I know. So it's not a big question, but I mean for something for students, it's a good exercise. There is also a question about unitarity. I mean, these local systems are unitary, but if you want to have unitary structure, you have also to pair chains. There is a question about unitarity. Of course, there is, if you think about Bigelow-Kramer, you have a question about the kernel of this representation. Do we get faithful? Part of the proof of Bigelow works, but not everything. But maybe something can be clever enough. And for you guys here, most involved in categorification, I mean, what about functorial action, similar functorial action on Fukaya category of configuration? If you remember about my model, there will be a basis represented by product of, there are a middle dimension, and there are product of simplices which are Lagrangian submanifold. So there are some technical points because you have boundary at infinity, and it's not easy in Fukaya Floor setup to deal with this, but guys, can you follow the picture and directly construct a functorial action? Okay, so I'm thinking done. Thank you so much.
Is there any questions?
Why you choose this specific Heisenberg group and the Heisenberg homology?
I show you this last relation. So this last relation was, I mean, it's an observation. So it was sigma 1 beta alpha. Beta, sigma 1 alpha. It was R here if you want. Let's say, yeah, sigma 1 equal alpha 1, sigma 1, beta 1. Say. R. Sorry, R. So if you I explained that if you make everything commutative, then it's not good. But if you just made sigma 1 central, so mod sigma 1 central, here you get sigma 1 square. Beta R alpha R equal alpha R beta R. And this is an Heisenberg relation.
Thank you.
Yeah. Like for the genus 1, do you get some kind of one-dimensional representation of double up and Heike algebras? Because
Double?
well, because mapping cloud, making
The representation in this case, I mean, one point is that the Schrödinger representation I gave is finite dimensional.
Right.
But it will not be faithful for this reason in this one. But I think that you could also work with the generic Schrödinger. In this case, I think it's you understand.
Well, my question was more like, in genus 1, is it like some other known construction related to this? Like I would imagine.
I should say that in genus 1 in particular, before even Kerler-Lubashenko, you had works of physicians like where it was more or less familiar.
Okay.
So there was something.
And for genus 2, is there like another, some kind of also special thing for genus 2?
I cannot say. By the way, we did computation, so we have a matrix, but it's not easy.
So you mentioned a relation to quantum SL2 if you sum over all n. If you don't do that and just keep n fixed or take n to be 0. Right. Do you know any superalgebra representation theory that?
If you restrict, I mean, with this version, if you restrict to just sub n, you will lose the quantum SL2 action because this quantum SL2 action shift n.
Not SL2.
Not SL2.
Something simpler.
I don't know.
No, but it's n into the weight space. It's just exactly the weight space. So usually the action moves the weight spaces.
The EF, yeah, but you want another action.
Yeah.
You have action of a mapping class group. I don't know. Even for n equal 2, it looks like a very rich representation of mapping class group. You have also interesting representation. If you don't ask unitary, maybe it's good to have representation with certain nilpotent thing. For example, the tautological representation or the regular representation. You can play with this. You can also untwist the regular representation. There is something to do, I don't know. But other action, I don't know.
If you take the usual break group for the plane with endpoints and compare it to the group of the tripod graph with endpoints on the tripod graph, is it the same group?
The group of the
tripod graph, just a graph with 3 edges emanating out of the vertex.
You can give yeah.
Is it the same group?
Yeah, it will be the same group. Yeah. You mean you get your disk,
Yeah, just take it. Yes.
remove points, and you take a graph skeleton.
No, I was thinking of just endpoints on a tripod graph, which is contractible. Tripod graph has 4 vertices and 3 edges connecting central vertex to the outer vertex.
4 edges and
4 edges, and so one trivalent vertex going out with 3 edges going out to univalent vertex.
Y-shaped.
Letter Y.
letter Y. So this is this is only 2. The surface.
Just letter Y, just
Y. Y here. Here you will get B2, yeah.
no, but for Bn, if you take endpoints.
Yeah.
Oh, you need many.
Okay, I didn't think a lot.
You need many edges. If you have n points, you need
You can see that locally here you can just push 2 points and.
But 1 is not enough. Just having one.
One would be enough, I think.
So y is enough for So y is enough for any number of points.
Yeah.
You can shift all
Yeah,
the
but,
points, shift them, and then.
Yeah, you do not. You need a base point, so you need to add. I mean, maybe the better picture is to say you put a vertex here, and you put a certain number of vertices here. You put n vertices here, and.
If you can realize the break group in this way, this is like a stack. This is like stack machine in computation like a context-free grammar. So
it looks like this.
You only have
sure,
one
sure.
extra thing where you keep an order. I'm thinking you can,
it looks like this.
It's like a stack.
Sure. So you see that here you can push this here, go here, come down.
That's exactly like the stack machine rules in
it looks like this here.
In computation. Because I mean, Varchenko and his collaborators has been writing about homology of configuration spaces in relation to quantum groups for at least 3 decades. Is there a kind of clear relation to the work of Lawrence, Bigelow, and others on that?
I will be
just because it's a huge body of literature
when
by.
You start to Google about configuration in graphs, you get references. People in combinatories of graphs, they are doing a lot. Yeah.
They have a book like back 3 decades ago, and many.
This is one of my motivations to connect what we know, what we are doing for surfaces, with all this combinatorial stuff coming from people in graph theory.
So the cobordism maps kind of have any specialization to Donaldson's TQFT or I don't know, the thing that you'd get just by taking kind of the exterior algebra on each one.
I don't see
corresponding to kind of just an abelian cover.
I should say that it's very near this abelian Chern-Simons theory, but there is a correction. And for you and people involved, the keyword here would be most Lagrangian correspondence. There is something with Lagrangian correspondence. You have elementary Lagrangian correspondence using just Lagrangian in H1. This will do something for the consistency. But you also have a story of Lagrangian correspondence in Fukaya-Fleur setting. And this is much more involved. And this is the idea for going to configuration. It's not done. It's not done. But I think I would go, there is some evidence that the good keyword would be Lagrangian correspondence. And you know the story.
If there are no further questions, let us thank Christian again.